Titrations. Unbelievable, and probably unbeknownst to most of you, we will be studying titrations in depth. Yes?
Back titrations.
No back titrations. No, we don't. But the reason why, and let me just say this to you now, is that we have to know what charge are going to be on our molecules. And by studying titrations first, we are going to it's going to help us understand what charge will be on our molecules. So we'll fully understand it. So let's start with the basics. Titration. In your burette, usually we have the base of known concentration, and in the flask, an acid of unknown concentration. And you added your base until we exactly reacted all of our acid and turned it a nice hue, right, with our phenolphthalein. And we can be vice versa. But at the equivalence point, we have added stoichiometrically. Remember coefficients. When I say that word stoichiometry, I mean we're looking at the coefficients in a balanced equation. So stoichiometrically, we've added the same amount of base as we have acid. Does not mean pH 7. Depends on the nature of the acid. Now, if we have a strong base and a strong acid, the pH at equivalence point will be 7. So when you did your titrations of sodium hydroxide against hydrochloric acid, the equivalence point was 7, and you used phenolphthalein as your indicator. But when we have a weak acid, our equivalence points will be analytical people. If you have a weak acid here, and we neutralize all of it, we're going to end up with the conjugate base in solution. So our solution will then be basic at equivalence point. I'm not going to ask questions like that, but I want you to recognize that it does not mean pH 7. And also, you have to look at the nature of the acid. Most of the time when we're titrating, we're looking at a monoprotic acid, that it just releases or ionizes one hydrogen ion. Does anybody know what a diprotic acid, or an example of a diprotic acid? H2SO4, so sulfuric acid is an example. Anybody know what triprotic acid? Yeah, phosphoric acid, H3PO4. So when we did our titrations, we added an indicator so that we could see that equivalence point. And at the equivalence point, our pH is going to change at a faster rate of change than at the other times. So here, if we could extend this, when you did the labs in general chemistry, you looked at the entire titration curve. You went past the equivalence point. You went to where the pH was very high. Here on this, I'm just showing you up to equivalence. So here we have acetic acid being titrated with sodium hydroxide. And what we have is an equivalence point when we add one equivalence of sodium hydroxide, because the stoichiometry is 1 mole of acetic acid reacts with 1 mole of sodium hydroxide. And so here we have an equivalence point. And we've fully reacted all of our acetic acid that's in our flask, and we've added exactly the same number of moles of our sodium hydroxide. So in solution, at this equivalence point, we only have our conjugate base. Now we say sodium, and the AC is our little shorthand for acetate. So right here, AC means this thing. So we have our counter ion would be sodium. You could write out sodium hydroxide here. So our counter ion for this anion would be sodium, so sodium acetate. At the midpoint, halfway, what we have is we've neutralized half of our acetic acid, and that has formed half the same amount, half of the amount of acetate. So we have equal amounts of the acid and conjugate base. So that at half of our equivalence point, we have our pH equal to our pKa. This is how the scientists figured out what a pKa was. So they would do a titration, find out where the equivalence point was, and then they would go to the half point and look at the pH of that. Here, it's 4.76 for acetic acid. So the pKa of acetic acid is 4.76. Now, to get the Ka, you would just do 10 to the negative 4.76. What do you notice in this yellow form? We're still adding sodium hydroxide, but what's happening to the pH? Not much. So what do you think we have here? A buffer. We have a buffer. Now, what we're going to do is we are going to look at these titration curves and figure out what's happening with our acid and base along this curve. So here, we're going to take our 1 molar acetic acid and our 1 molar sodium hydroxide. And if we have 100 mils of the acetic acid, and we've added 70 mils of sodium hydroxide, what do we have here? Well, we've added 0.07 moles of sodium hydroxide, and that's going to neutralize 0.07 moles of the acid. So what do we have left of the untitrated? We started out with 0.1 moles of acetic acid, because 100 mils of 1 molar is 0.1 moles. So let's put it in like 100. Like 0.1, we'll say that 100. And we've added 70 of sodium hydroxide, so we're left with 30 untitrated. So if you look back at so we started out with 100 of these. We've added 70 of these. So we're going to end up with 70 of this, and then the rest that's untitrated is going to be 30. Does that make sense to everybody? We start out with 100, and we add 70. 70 is going to be neutralized. So we produce 70 of this. What's left? 30. We started out with 100. We've neutralized 70 of it, so 30 is going to be left. So what we're going to do is look at our Henderson-Hasselbalch to help us calculate the pH at that point where we've added 70 mils of our sodium hydroxide. And the pH is going to be equal to the pKa of the acid plus, I would have to give it to you. Yeah, you are not to memorize any pKas. But on the homework, you can look them up or Google them, okay? And we've made 0.07 moles of our conjugate base, and we're left with 0.03 moles of our acid. So if you do that math out, we're at pH 5.13. Now, if you go back to the titration, okay, we can see that's where we're at, okay, at that many equivalents, or 70 milliliters of our sodium hydroxide added. If you go over to the pH, we're at pH 5.13. So you could, if you had a lot of extra time on your hands, and you knew the concentrations of the acid and the base that were added, you can construct a titration curve if you have a lot of extra time and not much else to do. We need to talk if that's what you're doing with your extra time. But remember, okay, so let's look at this. What do we have here at this point? What species, what thing do we have in solution? Just the base. We have just the base here. What do we have down here? Just the acid. What do we have here? Equal amounts of our acid and base. So what do we have more of here? We have more base. What do we have more of here? More acid. Do you guys want me to go over that again? Okay. When we start out, we only have the acid. So right down here, all HA. All HA. When we fully neutralize the acid, we have only the base. So up here at the end, at equivalence, we only have A minus, only the conjugate base. It's already written here to have equal amounts of your acid and base. So as we're getting more basic, going towards all base, we have more base than acid. As we're getting more acidic, right, towards the beginning of our titration, we have more acid. So all A minus, more A minus than HA, equal amounts of HA and A minus, more HA than A minus, and only HA. So as we're going through, you could say we start out with all HA, and we start neutralizing it. From the beginning, all HA, we start neutralizing it and producing some A minus until the point where we've neutralized half of it. Now we're neutralizing more than half of it, so we have more A minus than HA. And then we get all A minus, no HA left. We've just covered about a month of Chem 2, and but I need you guys to remember that the acid predominates at pHs below the pKa, and the base predominates at pHs above the pKa. So this is a take-home message. So you can see ionized, not ionized. Ionized above the pKa for the weak acid, not ionized below the pKa. That's a big deal. Buffers. A buffer is used when we need to maintain a consistent pH, when we might add more acid or base. And what we have is significant amounts of our weak acid and conjugate base. And so what we have to do is, when you prepare a buffer, is go into your prep room and find the acid and find the base, and then make up solutions and put them together. Okay? You have to have significant amounts of both. Usually the base is going to be a salt of that conjugate base. And so here we have an acid in conjugate base form. The metal is going to be something that's just a spectator ion that we're not going to really pay attention to. So we have the acid and its conjugate base, which is going to be the COO minus. So the difference between them is 1 proton. So never mind the metal when we're looking at buffers or acid-base conjugate pairs. So this is carbonic acid and sodium bicarb. Carbonic acid is H2CO3. The conjugate base is HCO3. They differ by 1 proton. Here, this is monobasic phosphate, sodium phosphate, and this is dibasic sodium phosphate. And so here we've we have more hydrogens here than we do here. So these are all acid-base buffers. So how does a buffer work? And you should put a big star on this, because we are going to talk about this quite a bit. A buffer works by chemically tying up an acid and base. So what I would do is I would give you a buffer. I would tell you, here's our buffer. Show me what happens when you add in acid. So what you'll do is you'll take the base part of the acid, of the buffer, and react it with the acid, the added acid, and produce the acid part of your buffer and water. And if I say, what does the buffer do when you add base? So then you're going to take the acid part of your buffer, you're going to show the added base, and you'll create the conjugate base and water. So what a buffer does is we have in a buffer an acid, a weak acid, and its conjugate base. If we add in acid, which part is going to be reacting with it? The acid or the base? The base, right? Acid doesn't react with the acid. The base is going to react with the acid. So maybe in your notes you would write base part of buffer. This would be the base part of your buffer. And then the H3O will be the added acid. And then over here, H2CO3, this is the acid part of your buffer, and water. So the base part of your buffer is going to react with added acid to create the acid part of your buffer in water. Now you might want to write down in your notes the acid part of your buffer. So here the H2CO3 is the acid part of your buffer. It's going to react with added base to produce the base part of your buffer in water. And so it's eating up any added acid or base. It can't eat up a tremendous amount. There's limitations. This is sort of a circle of buffers. So here, the conjugate base reacts with acid to produce the acid. The acid reacts with added base to produce the conjugate base. So what I will do is I will give you a different, and I do this every year. I'm telling you what one of the Part 2 exam questions will be. This is going to be the buffer. I'll tell you a different buffer. And you'll identify which is the acid part of the buffer and which is the base part of the buffer. And I'll say, give me the chemical equations, the reactions for how this buffer reacts with added acid and added base. So all you're going to do is take your different buffer and write these equations down. I tell people every year that I'm going to do that, and about 20% of the people don't do it. So if you don't understand this, please come see me, because it will be a question, and I'd love to help you out. Now, there's a limitation to a buffer. You have the pKa, where the ratio of the base to the acid is 1 to 1. Remember, we said pH equals pKa when they're equal amounts. But we will learn next time why it's only effective pH 1 above and 1 below. Hold on one second. So, guys, I don't know if the test is going to be next Tuesday. We're going to take our time. I think if I look at the... On Monday. It's scheduled to be